Good morning, students. Welcome you all to the online classes. Today I am going to discuss a chapter number 4 of class 11. The chapter number 4 is Principle of Mathematical Induction. So before starting this chapter, I would like to discuss some topics, some idea related to this chapter. So first thing is, what is the statement? What is the statement, or what is the mathematical statement? What do you mean by statement? So in mathematics, a sentence is said to be a mathematical statement if it is either true or false, but not the both. So a sentence is said to be a mathematical statement if it is either true or false. And mathematical statement is denoted by P, Q, R, etc., etc. So I am giving you some example of mathematical statement. For example, let us statement P equal to 2 plus 2 is equal to 4. So whether this is a mathematical statement or not, let's see. So obviously we know 2 plus 2 is equal to 4. So the answer of the question is true. This line is true. So it is a mathematical statement. If I write 2 plus 3 is equal to 7, so obviously this is not true, because 2 plus 3 is equal to 5, but it is given that 2 plus 3 is equal to 7. So it is also a mathematical statement, because answer of the sentence, answer of the statement is false. So whether the statement is true or false, it is called a mathematical statement. For example, I am giving another example. Suppose close the door. So whether it is a mathematical statement or not. So we can't answer the sentence in yes or no form. Means we can't answer the statement in true or false. We can't say that whether the statement is true or false. So it is not a mathematical statement. I am giving you some more example of mathematical statement. Suppose root 2 is an irrational number. So answer of this question is true. So it is a mathematical statement. If I say root 5 is a rational number, so we know that root 5 is an irrational number. So the answer is wrong, but still it is a mathematical statement. So I think you understand what is the mathematical statement. Means a sentence which has the answer in the form of either yes or no. That's called a mathematical statement. Okay, so now we define two more terms. One is the, what do you mean by deduction, and what is the induction. So deduction means, I am giving an example here. Suppose one statement is P, which is equal to human has 2 legs. Human has 2 legs. And let us consider another statement Q, Ram is a human. So obviously Ram has two legs. Means here the deduction means from a general statement we derive a specific statement. General statement means human has 2 legs, means all the human, generally case, all the human has 2 legs. If I choose a particular person, say Ram, so it has also 2 legs. So this conception is called deduction. Means when a specific thing is derived from a general thing. So this is called a deduction. What is the induction? That opposite of that. Means if you derive a general case from few specific case, then we say that this process is a induction. For example, Ram has 2 legs, Sam has 2 legs, Rakib has 2 legs, Mohit has 2 legs. and Ram, Sam, Rakib, Mohib, all are humans. So we can say that human has 2 legs. Understand, no? So induction means when a general thing is derived from some particular specific things. So this process is called induction. Now our chapter is mathematical induction. So what do you mean by mathematical induction? So the definition of mathematical induction is: mathematical induction is a process or tool that prove a sentence whether it is true or false. So mathematical induction is a tool or process which prove a sentence to be true or false, okay, or which prove a sentence. Okay, now we'll discuss the mathematical principle of mathematical induction. It is a very important thing. Principle of mathematical induction. Principle of mathematical induction. Principle of mathematical induction. What do you mean by principle of mathematical induction? The principle is, suppose a statement P of n which is true for n equal to 1. The statement is true for n equal to 1. And second condition is, if the statement is true for n equal to k, where k is any natural number, then if the statement is true for n equal to k, where k equal to k is an arbitrary natural number, then the statement is true for n equal to k plus 1. Means if the statement is true for n equal to k, then the statement is true for n equal to k plus 1. Then the principle of mathematical induction says that the statement is true for all values of n. Then the statement is true for all values of n. So principle of mathematical induction says that if a statement P of n is true for n equal to 1, and if the statement is true for n equal to k, then the statement is true for n equal to k plus 1. I am giving an example. Let us consider a mathematical statement as P of n equal to P of n such that the sum of first n natural number which is equal to n into n plus 1 by 2, n into n plus 1 by 2. So this is a mathematical statement. Now using the principle of mathematical induction, we will prove that the sum of first n natural number is equal to n into n plus 1 by 2. So we have to follow 2 steps. First is, we have to check whether the statement is true for n equal to 1 or not. If the statement is true for n equal to 1, we'll consider that the statement is true for n equal to k, and hence we will prove that the statement is true for n equal to k plus 1. Then we can say that the statement is true for all values of n. Now see first condition. Now if I put for n equal to 1, if I put n equal to 1, so the left hand side will be 1. Now P of 1, what do you mean by P of 1 or P of n? P of n means the sum of first n natural number. P of 2 means the sum of first 2 natural number, that is 1 plus 2. P of 5 means the sum of first 5 natural number, that is 1 plus 2 plus 3 plus 4 plus 5. P of k means the sum of first k natural number, means 1 plus 2 plus 3 plus 4 plus dot 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 plus k up to kth term. So the P of 1 means if I put n equal to 1, so the left hand side will be the first term only, that is 1, and the right hand side will be put n equal to 1 in the right hand side, so it will be 1 into 1 plus 1 by 2, that is 1 into 2 by 2, 2 and 2 will cancel each other, so that is equal to 1. So for n equal to 1, the value of the left hand side is equal to the value of the right hand side, means left hand side and right hand side are equal. That means the mathematical statement is true for n equal to 1. Then write, therefore a P of n is true for n equal to 1. So first condition is done. Now second condition is we consider that this statement is true for n equal to k. So let P of n is true for n equal to k, means we are considering that this mathematical statement is true for n equal to k. Now as it is true, then P of k will be 1 plus 2 plus 3 plus dot 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 plus k, means sum of first k natural number, which will be equal to k into k plus 1 by k into k plus 1 by 2. Now with the help of this result, we'll prove that the statement is true for the k plus 1 value also. Now we'll consider this expression P of k plus 1. Now if we can prove that the statement is true for k plus 1 also, then we can say that by principle of mathematical induction that the statement is true for all values of x. So P of k plus 1 means the sum of first k plus 1 natural number, that is 1 plus 2 plus 3 plus dot 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 plus k plus 1, the sum of first k plus 1 natural number. So can you say what is the previous term of the last term? Previous term of the last term, look here, the numbers are increasing gradually one by one, so its previous term will be k and then k plus 1. Now see this term, the value of this portion is known, which is equal to k into k plus 1 by 2. So put the value k into k plus 1 by 2 plus k plus 1. Clear? Now I'm using this portion. So now from this two we can take k plus 1 common. So if I take k plus 1 common, so remaining part will be k by 2 plus 1. Okay, that is equal to k plus 1 into, do the LCM, so it will be k plus 2 by 2, k plus 2 by 2. Now we'll just rearrange this term in the form of that. So k plus 1 into, now k plus 2 can be written in the form k plus 1 plus 1 by 2. So now look, this result and this result both are looking same, where n equal to k plus 1, n equal to k plus 1, or you can do like that, use a second bracket. So if I put n equal to k plus 1 in this expression, so it will be look like that. That means we can say that the statement is true for k plus 1 also, means P of k plus 1 can be also expressed in the form k plus 1 into k plus 1 by 2. That means the statement is true for k plus 1 also. So look, the statement is true for n equal to 1, and if the statement is true for n equal to k, we prove the statement is true for n equal to k plus 1 also. Then by principle of mathematical induction we say that the statement is true for all values of k, and henceforth. So look at the procedure once, because all the problem in this exercise can be solved this way. All the problem, whatever the problem it is, we can solve the problem this way. So I am telling you the procedure once again. First we will consider the given expression as p of n. So p of n equal to the given expression. Next step, what we would have to do, just we'll have to check whether this expression is true for n equal to 1 or not. If the statement is true for n equal to 1, because the left hand side and the right hand side are equal, that means the statement is true for n equal to 1. Now we'll consider that the statement is true for n equal to k, and with the help of this line, with the help of this condition, we'll prove that the statement is true for n equal to k plus 1. Then we can say that by principle of mathematical induction that the statement is true for all values of n. This is the procedure. Okay, so let's start a few problem from your exercise. There is just only one exercise, 4.1, and we'll going to solve few problems, and you can see that all the problems has the same procedure. Okay, so let's start question number 1. Question number 1 is prove that by principle of induction 1 plus 3 plus 3 square plus 3 cube plus dot 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 plus 3 to the power n minus 1 is equal to 3 to the power n minus 1 by 2. 3 to the power n minus 1 by 2. So we have to prove by using principle of mathematical induction that this expression is equal to 3 to the power n minus 1 by 2. So first what I have to prove? So we'll consider let the given expression as Pn equal to the given expression. Now for n equal to 1, we'll check whether the statement is true or not. So put n equal to 1. So for n equal to 1, what is the value of the left hand side? Value of the expression on the left hand side? P upon means P upon means the first term, and that is equal to 1. What is the right hand side? What is the value of the right hand side? Put n equal to 1. So 3 to the power 1 minus 1 by 2, which is equal to 3 minus 1 by 2, and that is equal to 2 by 2, which is 1. That means the value of the left hand side and the value of the right hand side both are equal. That means we can say that the statement is true for n equal to 1. Statement is true for n equal to 1. Now we'll consider let the statement is true for n equal to k. Let the statement is true for n equal to k. Now since the statement is true for n equal to k, that means p of k will be equal to means 1 plus 3 plus 3 square plus dot 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 plus 3 to the power k minus 1, which will be equal to 3 to the power k minus 1 by 2. As the statement is true for n equal to k, so this condition. Now we'll prove that consider that the expression p of k plus 1, which is equal to the sum of first k plus 1 term of this expression, which is equal to 1 plus 3 plus 3 square plus dot 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 plus 3 to the power k plus 1 minus 1, and plus 1 and minus 1 will cancel, k plus 1 and minus 1. So this one and this one will cancel each other, means it will be 3 to the power k. Now if I rewrite this line again, so 3 plus 3 square plus dot 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 dot, and last term is 3 to the power k. What will be the previous term of that? So it will be 3 to the power k minus 1, because look at the power, this is 3 to the power 0, which is equal to 1, this is 3 to the power 1, this is 3 to the power 2, and then 3 to the power 3, 3 to the power 4, and dot dot dot, means power of the 3 are gradually increasing by 1. So as the last term is k, so previous term will be 3 to the power k minus 1. Now look at that portion whose value is already given here, which is equal to 3 to the power k minus 1 by 2. So if I continue this line, so it will be 3 to the power k minus 1 by 2 plus 3 to the power k. Now do the LCM. LCM is 2, so it will be 3 to the power k minus 1 plus 2 into 3 to the power k. Okay, now look, this 3 to the power k plus 2 into 3 to the power k together give 3 into 3 to the power k minus 1 by 2. That means 3 to the power 1 and multiplied with 3 to the power k means 3 to the power k plus 1 minus 1 by 2. Now look, this expression and this expression which are identical for n equal to k plus 1. So can you say that the statement is true for k plus 1 also? That means the statement is true for n equal to k plus 1 also. That means the statement is true for n equal to 1, and if the statement is true for n equal to k, we have proven that the statement is true for n equal to k plus 1 also. That means by principle of mathematical induction we can say that the statement is true for all values of n, and hence proved. I am giving one more example. Suppose question number 4. Question number 4. So look at the question once. The problem is 1 into 2 into 3, 1 into 2 into 3 plus 2 into 3 into 4 plus dot 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 dot, and the last term is n into n plus 1 into n plus 2. We have to prove this is equal to n into n plus 1 into n plus 2 into n plus 3 by 4. N into n plus 1, n plus 2, n plus 3 by 4. We have to prove this one. Now what we have to do? First we have to consider let the given expression as p of n. So p of n equal to 1. Now we have to prove whether the statement is true for n equal to 1 or not. So put for n equal to 1, the left hand side will be, put n equal to 1, so first term will be 1 into 2 into 3, and if I multiply, so the result will be equal to 6, and the value of the right hand side, that is 1 into 1 plus 1 into 1 plus 2 into 1 plus 3 by 4, which is equal to 1 into 2 into 3 into 4 by 4. 4 and 4 will cancel each other, so is same. So for n equal to 1, the value of the expression in the left hand side and the value of the expression on the right hand side are equal. So we can say that the statement is true for n equal to 1. Next step, we will consider the statement is true for n equal to k. We are considering this, that the statement is true for n equal to k. So since the statement is true, so value of p of k means the sum of kth term of this expression means 1 into 2 into 3 plus 2 into 3 into 4 plus dot 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 dot. The last term will be k into k plus 1 into k plus 2. It will be equal to k into k plus 1 into k plus 2 into k plus 3 by 4. K into k plus 2 k plus 3 by 4. This is true for n equal to k. This statement is true. Now with the help of this line, this condition, we have to prove the statement is true for n equal to k plus 1. So for that we are considering this expression p of k plus 1, which is equal to 1 into 2 into 3 plus 2 into 3 into 4 plus dot 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 dot. The last line will be in place of k put k plus 1. So k plus 1, k plus 2, k plus 3. Okay. Now can you see what will be the previous term of the last term? So previous term will be 1 into 2 into 3 plus 2 into 3 into 4 plus dot dot dot. Previous term will be k into k plus 1 into k plus 2 plus the last term means k plus 1 k plus 2, k plus 3. Okay, I'm rubbing this portion. Okay, now value of the expression up to this is known here. This is equal to this expression. So in place of this we can put k into k plus 1, k plus 2, k plus 3 by 2 so it's not 2, it is 4 plus k plus 1, k plus 2 into k plus 3. Now from these two expression we can take k plus 1 into k plus 2 into k plus 3 common. So if I take this expression common, so it will be k by 4 plus 1. Now add this. So if after adding it will be, if I add them, so LCM will be 4 and it will be k plus 4. Now if I rearrange this statement, this condition as k plus 1 into, now k plus 2 can be written in the form k plus 1 plus 1, k plus 3 can be written in the form k plus 1 plus 2, and k plus 4 can be written in the form k plus 1 plus 3 by 4. So look, we can say that this statement is true for n equal to k plus 1 also. Then by principle mathematical induction we can say that the statement is true for n equal to k plus 1, and hence we can say that the statement is true for all values of n. Okay, so today I have done two questions, question number 1 and question number 4. So next day we'll solve a few more problems from this chapter. I hope you understand this one, and do one thing, try to solve question number 2 and 3 which I have not done here, and next day we'll solve the remaining problem. Thank you.